Let's see this problem. A system uses 3 frames for storing pages of a process in main memory. So they're saying that, see, we have RAM, right? Coming to RAM, we will have lot of pages. Fine, we will have lot of pages. Now out of these many, we will have lot of frames. Out of these many frames, 3 frames are allocated to our process. Okay, we are considering a single process over here, and they told that they have allocated 3 frames for this process. Let us assume these are the 3 frames which are allocated for this process, right? See, these frames can be allocated non-contiguously, right? We have already seen it. But just for simplicity, just to solve this problem, just to understand this problem better, I am assuming that these 3 frames are allocated for process P1. Fine. It uses the least recently used page replacement algorithm. Now let's see about least recently used a bit later. What is the total number of page faults that will occur while processing the page reference string given below? They have given the page reference string. Now what do we mean by page referencing? See, they are asking the number of page faults, right? Now what do we mean by page reference string? These are the pages. See, the process can have a lot of pages, right? A process can, let us assume this process is having pages like page number 0, page number 1, page number 2 and so on. It has a lot of pages, right? And these are the set of pages which are referred by CPU in this order. And one more point you need to understand here is CPU will always request for a byte, right? Byte or word. It will not request for a page. But now why have I given these pages rather than bytes or words? The reason I have given this is it means that CPU is requesting for a byte in page number 4. Then CPU is requesting for a byte in page number 7 of process P1, right? We are considering only one process. Let us assume the name of the process is P1, just for simplicity, okay? Now this is what they have given. CPU is initially requesting for page number 4 of process P1, page number 4 of process P1. Then CPU is requesting for page number 7 of process P1. Then it is requesting for page number 6 of P1. Then it is requesting for page number 1 of P1 and so on, right? Fine. And also they have told that 3 frames are allocated for process P1. Now they are asking, in case if we are using least recently used page replacement algorithm, how many page faults will happen? What do you mean by page faults? How many times are we accessing the CPU, are we accessing the hard disk in order to get the page, right? That's what we mean by page fault. Fine. Anyway, also they have given that we are using demand paging. What do you mean by demand paging? Demand paging means we will not load any page until CPU requests for a byte in that page, right? Fine. So initially these frames will be empty. This is a RAM, right? Initially these 3 frames will be empty, which means before processing this page reference string, we will not load any page in these frames. Why? That's what we mean by demand paging, right? Only after this page is requested by CPU, we will load this page inside the RAM. We will not load it before itself, right? That is what we mean by demand paging. And one more important point, every page will lead to at least one page fault, right? Because we are not loading that page before CPU requests for that page, right? Before CPU requests for a byte in that page. Fine. Now what do we mean by least recently used algorithm is, see, let us assume initially CPU is requested for page number 4, right? Page number 4. Now since we are using demand paging, page number 4 will not be definitely present inside the RAM. Why? Because this is the first time page number 4 is requested. Initially all these 3 frames allocated for process P1 will be empty, right? Fine. Now since page number 4 is requested by CPU, I am going to load page number 4 inside the RAM, right? Fine. Now CPU is requesting for page number 7. Page number 7. See, these are the 3 frames which are allocated for process P1, right? Now since I have free frames, what I will do is I will place it here. In case if I don't have free frame, I will replace one of the pages, right? One of the frames. Anyway, let's see that. Then CPU is requesting for page number 6, right? Since I have a free frame, I will allocate it here, right? I will place page number 6 over here. Fine. Now CPU is requesting for page number 1, right? Now comes the problem. CPU is requesting for page number 1. Now we don't have any free frame for process P1, right? So in this scenario, we might have to definitely go for page replacement. which means we might have to replace one of these 3 pages in order to place page number 1, right? We need to replace one of these 3 pages with page number 1. Now which page are we going to replace among these 3 pages? That is the most important point, right? That is being decided by page replacement algorithm. That is being replaced by page replacement algorithm, and they have given that coming to this problem we are going to use least recently used page replacement algorithm. Now least recently used page replacement algorithm means we are going to replace the page which has been referred by the CPU long back, or which has not been referred by the CPU in the recent times, right? See, we are now processing this page, right? This is the page we need to place inside the RAM. Now we are actually processing page number 1, right? We need to place page number 1 inside the RAM. Now see the page reference string before. We have referred page number 4, page number 7, page number 6. Now this is which is the most recently referred page by CPU? Page number 6, right? Page number 1 is obviously referred now, fine. Now before this, the most recently referred page is page number 6, right? And before that page number 7 is referred, and before that page number 4 is referred by CPU, right? Now out of these 3 pages, the most recently referred page is page number 6, fine. Now the least recently referred page is page number 4, right? This is the page which has not been referred for a long time, right? Out of these 3 frames. This is the frame which has been referred recently. This is the frame which has been referred before page number 6, and this is the frame which has been referred before page number 7. So page number 4 is the least recently referred page by CPU, or least recently used page by CPU. So since we are using least recently used page replacement algorithm, we should definitely replace page number 4 with page number 1, right? Which means we have taken this page number 4 and we have placed page number 1 inside the RAM. Fine. Now CPU is, this is now fine. This is definitely a page fault, right? Why? Because we are taking page number 1 from the hard disk and then we are placing it in the RAM. Even these are also page faults. Why? Because we are using demand paging, and while referring page number 4 we placed inside the RAM, and while referring page number 7 we placed inside the RAM from the hard disk, while referring page number 6 we placed inside the RAM. All these 3 are page faults. Also this is also a page fault because we placed page number 1 from the hard disk into the RAM, right? Replacing page number 4. Fine. So as of now we have 4 page faults, right? Fine. Now let's see this. This is done. Now they are asking for page number 7. Now one important point you need to observe here is, will this lead to page fault or not? This will not lead to page fault. Why? Because page number 7 has been already present inside the RAM, right? Page number 7 has been already present inside the RAM. So there is no point in accessing the hard disk over here. So accessing time will become very less because we can straight away take the byte in page number 7 from the RAM, right? So this is what we should be targeting mostly in page replacement algorithm, which means whenever CPU is requesting for a word, in case if the page containing that byte is present in the RAM, it will become very easy. So we should always try to have the page inside the RAM which CPU will refer next, right? This is not always possible, but we will try to achieve it as much as possible. Fine. Anyway, we will understand it a bit later, okay? Once we see 2-3 examples, you will understand it. See this. As of now, CPU is requesting for page number 7. Fine. It will not lead to page fault, right? It is already present in the RAM. Fine. Now CPU is requesting for page number 6. Again, page number 6 is also present in the RAM. It will not lead to page fault, right? It will simply take the byte from the RAM and then it will execute it. So until this point, one thing you need to understand is we have only 4 page faults, right? Initially for page number 4 it led to a page fault. Page number 7 it led to a page fault, page number 6 it led to a page fault, page number 1 it led to a page fault. 1, 2, 3 and 4. Now after this, these 2 are not page faults, right? They are page hits. We can say that as page hits. Fine. Now this is done. Now CPU is again referring for page number 1. Again, page number 1 is present inside the RAM, right? There is no page fault. Now page number 2 is referred by the CPU. Page number 2 is not present inside the RAM, right? So definitely page number 2 has to be moved into the RAM. But no free frame is present, right? All the frames has been allocated. Only 3 frames are allocated for this process, and these 3 frames has been already occupied. Now what we should be doing is we should do page replacement, which means we should replace one among these 3 pages with page number 2. Now which page should we refer? That depends, that is being decided by page replacement algorithm, and we are using least recently used page replacement algorithm, right? Now see, as of now we are referring this point, right? Now out of this reference string, we need to search, we need to check for the page which has been referred, which has been referred long back, right? Fine. See this, page number 1 is the most recently referred page, right? It is not the least recently referred page. As of now we have page number 1, 7 and 6, right? Out of which page number 1 is the most recently referred page, and page number 6 has been referred a little earlier, right? Little earlier. Now page number 7 is the least recently used page or least recently referred page by CPU, right? See, out of these 3 pages, page number 7 is the least recently used page, right? These 2 pages are referred recently, but this page has not been referred recently, it is referred long back. So what we should be doing is we should replace page number 7 with page number 2, right? It is leading to one more page fault. As of now we have 5 page faults, right? 1, 2, 3, 4, 5. Fine. Now this is done. Now the CPU is requesting for page number 7. Just now we moved page number 7 out of the RAM, right? So anyway we need to move page number 7 from hard disk to RAM one more time. There is no other way, because page number 7 is not present inside the RAM, right? So page number 7 has to be moved into the RAM. Fine. Now which page should we refer here? Which page should we replace here? That depends on which is the page which has been least recently used, right? See, we need to check this string, right? As of now we need to check this complete string in order to place page number 7 over here. 2 is the most recently referred page, fine. 1 is again referred recently, fine. Page number 6 is the least recently used page, right? Which means this is the page which has been referred long back by CPU or which has been not referred recently by CPU among these 3 pages, right? So page number 6 has to be replaced with page number 7, right? Fine. Now CPU is requesting for page number 2. Page number 2 is already present in the RAM, so there is no page fault, right? So CPU can directly take this byte from page number 2 and execute it. So what is actually happening here? What is the number of page faults over here? Here there are exactly 6 page faults. You can count all these things, including the strikes and the pages which are present, right? 1, 2, 3, 4, 5, 6. So the number of page faults over here is 6. Number of page faults over here is 6. See, coming to here, we have used least recently used page replacement algorithm, right? We also have other page replacement algorithms. We have something called as first in first out page replacement algorithm. We have something called as most recently used page replacement algorithm. We have a lot of page replacement algorithms. Now my question is least recently used page replacement algorithm the best algorithm for this problem or not? We can't really say this. Why? Because we need to check other algorithms as well, right? See, coming to this algorithm, coming to this problem, in case if I'm using least recently used page replacement algorithm, we are getting 6 page faults, right? Now in case if I can find an algorithm, some other algorithm, say algorithm number A, I'm just naming it, right? Algorithm name A. In case if that algorithm has 5 page faults, definitely that algorithm is better than this algorithm, right? Why? Because we need to have the number of page faults as less as possible. Why? Because page faults are actually going to decrease the CPU efficiency. Why? Because page faults is going to increase the accessing time, right? In case if I have page fault, I might have to access the hard disk. Now in case if I access the hard disk, my CPU might have to wait for a long time to get the byte, right? That is ultimately going to degrade the performance of CPU. So we need to have the number of page faults as less as possible. Here, coming to a least recently used page replacement algorithm, we are getting 6 page faults. In case if I can find some other algorithm which has 5 page faults or 4 page faults or whatever, I can say that that algorithm is better than this algorithm, least recently used page replacement algorithm. In case if I have an algorithm where the number of page faults is greater than 6, let us say it is 7 or 8 or 9. In that case, we can say that least recently used page replacement algorithm is better than those algorithms, right? So the main idea of page replacement is we need to see that the number of page faults should be as less as possible, right? So that it will increase the CPU efficiency. See, everything we are seeing here in memory management is done to do two things. One is time management, another one is space management. What do you mean by time management? We are increasing the CPU efficiency, right? In case if CPU efficiency is higher, our computer will be very fast, right? So in that case, we are actually consuming time. Time complexity is better. Whereas we are also taking care of space complexity, right? Which means space complexity means we are making use of the space in the RAM in the most efficient way, right? That is what we mean by space complexity. Anyway, time complexity and space complexity is not important here. We'll see in algorithms and all this. What I want to tell you is the main intention behind page replacement algorithms is the number of page faults should be as lesser as possible. The algorithm, among all the algorithms, the algorithm which gives the least number of page faults should always be preferred compared to the algorithms which gives more number of page faults. Fine. So the answer for this question is 6. Okay, we have already done it. I am giving extra insights just to understand it clearly. I think you understood what is meant by demand paging, right? We are not going to load any page before CPU requests for a byte in that page. What do you mean by page reference string? Page reference string means these are the pages which are referred by the CPU in that order, right? Page number 4 followed by page number 7 followed by page number 6. Fine.